So here we have a rectangular swimming pool and it's filled to 1 foot below the top. We want to figure out how much work is required to pump all the water into a drain at the top edge of the pool. So it's a rectangular pool. It's 8 feet deep, 10 feet wide, and 20 feet long. So basically we can think about it as being a rectangular prism like this. Where it is, so it's 8 feet deep, 10 feet wide, and 20 feet long. Okay, and then it's full of water to 1 foot below the top, so it's it's filled to a height of 7 feet. So a bunch of water in there. Okay, and we want to figure out how much work is required to pump all the water to the top of the pool. So what we're going to do is we're going to label the x-axis will actually be vertical here. The bottom, I'm going to call that x equals 0. The top, I'll call that x equals 8. Of course, x equals 7 is going to be important because that's where the top of the water is right now. And then we're going to think about taking all of the water at a particular x value there. Okay, taking a slice of that water all at a particular height. How much work is required to take that amount of water up to the top? Okay, so at a particular x value, all the water at that height is going to be a rectangle. Okay, so each slice at height x is rectangular, with area. What's the area? Well, the area, it's going to be it's a 10 by 20 rectangle. So 10 by 20 is 200, so it's going to be 200 square feet. And we do have to consider the thickness. And since it's we're considering it a very thin slice there, we can call the thickness delta x or even dx if we want to. Okay. Okay, so how much work is required to pump that slice to the top? So the work for each slice, work is force times distance. The force is just the weight of the water, which is going to be 62.4 pounds per cubic foot times 200 delta x cubic feet, right? That's basically density times volume. Density times volume gives you the weight. Okay. Then the distance, how far does it have to go? Well, it's got to go from a height of x to a height of 8, so that distance is going to be 8 minus x. Okay, so let's see, 62.4 times 200 is 12,480. So this is 12,480 times 8 minus x times delta x. right? That's, so whatever the thickness is and whatever the height is, that tells you the work required to pump that slice of water to the top. Now we need to pump all of the slices to the top from, and there's a slice for every single x between 0 and 7 that needs to move to the top. So the total work is going to be the integral from 0 to 7 of that function that we just found. Except the delta x is going to become a dx here because we're adding and we're thinking about them being infinitely thin. So that's going to be, so the 12,480 is a constant. It can come out front. The integral of 8 minus x is going to be 8x minus x squared over 2. And that's evaluated from 0 to 7. So what we have here is that, that 12,480 times 8 times 7 minus 7 squared over 2, which is 393,120. So 393,120, and that is foot-pounds.